anyways, what I want to talk about is give a brief introduction to MnTAP. Many people, how many people know what MnTAP is? Few, but fair number that sound like they don't. So I'll try to give a little bit of introduction to MnTAP, talk a little bit about what our wastewater activities have been, and then talk about our grant project and some of the assessment findings, concentrating on things related to oversized equipment, DO control, and also want to talk about an energy tool, basically an aeration process model that can help evaluate what the impact of changes can be next. So, anyways, the Minnesota Technical Assistance Program is a program at the University of Minnesota. It was created in 1984. Primarily what we do is provide waste management, pollution prevention, and some energy efficiency outreach, assistance, promotion to Minnesota manufacturers and process industries or process facilities, and wastewater treatment plants do fall into that. We are non-regulatory. We can't order anybody to do anything. Everything that we do is presented in a justification of why it makes sense for the facility to take action, but it's up to the facility to make a decision on whether it actually makes sense to them. And we're also confidential. Next. So some of the services that we provide are essentially on-site assistance, trying to help solve a problem or make an improvement, process improvement. We've got an intern program where we place engineering students at a facility to solve a problem that the facility is interested in, and we're paying 2/3 of that intern cost, as well as giving some support. We also do some team facilitation where we help participate and make sure that a team at a facility is running well and effectively. We've got a number of resources, a website that contains a fair amount of information that we like to think is useful. There is a DOTW webpage, and they contain fact sheets and case studies and examples. We also operate the Minnesota Materials Exchange, which is essentially a matchmaking service trying to match up facilities that have surplus materials with facilities that have use for those surplus materials so that they don't enter the waste stream. Next. So the kinds of things that we've done for wastewater plants or in conjunction with wastewater treatment plants is we've given assistance to their customers at the request of the wastewater treatment plants in many cases, where we're looking at industrial wastewater loading reductions. If you can identify a problem input for you and have a good sense of where that's coming from, and if there's an incentive for the facility to act, some costs that would be coming. In some cases, we can make a case that it's just they're part of the community and taking actions, even that if there's a small cost, can be useful. We've also got a solid waste grant project that's going on right now. If there are plants that would see food waste from places like restaurants and institutional, looking at trying to divert some of that material, it's a possibility that your interest could fit in with that. That project is aimed at working with counties, but it will ultimately take place in a locality. And if you have an interest, let me know. We can talk about whether there's a way that it can positively help you. We've also given some assistance to plants directly. We've got the DWTS webpage that has some resources. Our past director was involved with quite a number of plants assisting on phosphorus management plans. We've got the intern program where we've had interns at 3 different plants. Had a couple of projects at the MCES Metro plant looking at energy reduction. We had a project in Rogers looking at DO control. And we've got a project in Hutchinson right now where the intern is looking at essentially trying to make use of excess plant capacity and the possibility of setting up an ox zone in an oxidation ditch to essentially achieve some measure of denitrification and at the same time reduce energy consumption for the plant. Next. And then the other kind of direct assistance has been under this EPA grant that we're in the kind of the final stages of, where we were looking at electrical energy conservation, trying to identify opportunities. We're looking at pretty much purely electrical energy conservation. That's the major energy utility at wastewater treatment plants, and we were looking at the activated sludge plants that have aeration processes. And we tried to identify changes that had significant enough estimated savings where they were worth evaluating further, or in some cases some relatively simple changes that could be done without cost and have been implemented. Next. One of the things we did in this process is we looked at process benchmarks, electrical benchmarks, and this is essentially for a number of plants the benchmark that we've seen of essentially the kilowatt hours per year per day divided by the million gallons of water processed. And there is quite a range, and that reflects some degree the variation in process flows or the unit operations in a plant. And we tended to concentrate on plants that had higher energy benchmarks on the theory that there was more opportunities there. We did see in our survey benchmarks as low as 2,000 kilowatt hours per million gallons processed. And the Wisconsin Focus on Energy did some work 5 or 10 years ago in Wisconsin, and the best quarter of plants there had a threshold of 1,300 kilowatt hours. But so per gallon of processed, we're seeing 4 times the energy used, 4 times the electrical cost for some plants. So we'll go to next. And then we also looked at that benchmark and kind of broke it down within the plant to identify where in the process that electrical use was found. And again, it reflects a lot the different kinds of operations that are going on, and there are reasons for some of the differences. But what we found was that secondary treatment, or essentially the aeration process, was a big part. Typically, it was 50% of the electrical use. So the red numbers are the plant total. So we've got the 2,000 at one plant that was less than half of that. It had a trickling filter was a big part of why that, I think, plant had low energy. The sludge processing tended to be another process that was somewhat high. And then this plant had the ATC process to create a Class A sludge, and that's a fairly energy intensive, so that raised their benchmark up. Next. One of the things that we found as a general theme was that a lot of the plants were operating at quite a ways less than plant design capacity. So the one with the most over capacity was operating at about 24% of design capacity, and we did have a couple that were in the 75 to 85% capacity. And the reason that that's significant is that we saw a number of situations where some of the equipment was quite oversized. So next. And one of the areas where we saw oversized equipment was in the blowers. So we had one plant that was using positive displacement blowers. They were almost always operating at the lowest speed, and even at that lowest speed, lowest error output, 80% of the time DO was at 4 milligrams per liter or higher, and there was 40% of the time where it was above 8. And we estimated the cost of essentially the oversized blowers was around $8,000 a year for that. Second plant had centrifugal blowers. Inlet valves were always 50% open or less. This one had a smaller estimated savings, around $1,400. The last plant was an SBR plant with centrifugal blowers. Inlet valves were always at minimum, and as the aeration cycle in the SBR went through its cycle, 10% of the time the DO was higher than 4 milligrams per liter. And we estimated the cost of oversizing there was at about $8,900 a year. And this is a plant that is in the process of working to, I guess, correct the oversize or put in a smaller blower. Next. I guess the reason that or that oversize is an issue is this is basically taking blower curves from the centrifugal blower and basically putting them in a different output, basically putting it as CFM per horsepower, or how much air are you getting for the power input. And essentially at 100% for these particular blowers, for the top curve, the minus 30-degree curve, you're almost 25 CFM per horsepower. Down at the bottom of its useful or operating range, it's almost half of that, or around 13 CFM per horsepower of input. Next, and let's see. I guess let's go next one more time. I had intended to take that one slide out, but this puts that same curve on the format of what does it cost to generate or to produce 1,000 CFM. And so at this end of the curve, that blower is able to produce a lot more CFM, but per CFM, per 1,000 CFM, the cost here is about $350. At the bottom of the curve, it's almost twice as expensive to get 1,000 CFM. The capacity has definitely changed, so there's definitely differences. And I guess the point I'm trying to make is that while wastewater is inherently a variable process, you have to adjust or want to adjust to the conditions in your plant. It's useful to know what the cost of that is, and ideally you've got a system that's designed to operate efficiently at the conditions that you want to operate. And my recommendation would be to try to avoid this end of the curve and try to operate in the more efficient half of the curve, but basically know what the costs are. Okay, next. Another place where we saw oversized was in some of the UV disinfection systems. Again, they're designed for the essentially peak flows and are supposed to work for that. And if at this plant the typical flows were 30% of design, so that would imply that there's a lot more capacity in that UV system. But initially, all the lamps were lit and were running. They cut the power to 50% of the lamps and saved about $17,000. And we're essentially getting the same disinfection rates. Next. So anyways, how do you correct for oversize? I guess these are my thoughts, and would be certainly interested in getting some thoughts of you. But just to give me a sense of who's in the audience, how many people are involved with operations or management at wastewater treatment plants? And how many are involved with essentially the design or building of plants? So mostly operators, a couple of designers. I guess the thoughts that I have are, once the plant is built, it is somewhat it can be expensive to correct oversized problems. So the ideal place to make sure that the plant isn't oversized is when it's being built. And I guess my suggestions for operators are starting off with to know what your energy benchmark is, so that you've got a point of comparison for what the design of a new plant might be. And then I guess the other thing would be to require or ask your designer, in addition to giving you the capital cost, what are the operating costs in terms of a benchmark, in terms of dollars per million gallons of water processed, kilowatt hours per million gallons processed, and to do that at what it is at peak. The plant's got to operate there. What are your operating costs at peak? What are your operating costs at the design loads or flows? This, I think, is an important one. What's going to happen when the plant starts? What are the operating costs? And are they a lot higher when you're not at design flows? And then if there are some significant intermediate steps, we'll look at that. For designers, I would hope that they would offer that service to look at operating costs and look at essentially life cycle costing of the plants. And in terms of how to adjust the design, I guess I would start off making sure that it runs efficiently at current flows and loads. And then based on what we've seen in this project, we would suggest looking at modular additions. So rather than having two large blowers that each can handle the peak load, have one that handles the current load now, and be able to add small blowers in succession. And it's certainly going to increase the capital cost, makes some things complex, a little bit more complex, But I guess I would argue that, and I guess the question would be, how big of an impact is that per year spread out through the financing of the plant compared to what it might save in terms of yearly operating costs. Some other strategies that can be used is looking at having units that can be base loaded, essentially run full, and then have one that is able to do trim. So in terms of blowers, the turbo blowers are expensive, but they work very well, very efficiently over the full range of their operation. So can you mix and match? Have some centrifugal blowers that run efficiently when they're run full out, or positive displacement blowers, and have a single turbo blower that's operating in trim, or have a range of capacities that where you can select what works best. But again, try to avoid and know what the low efficiency, high cost areas of the operating equipment is, and try to avoid that. So next. I guess the next thing I wanted to do was talk a little bit about an aeration model. One of the pieces for our project was to offer training, and we brought in Steve Bowles, who's a consulting engineer from New Hampshire, who's done a lot of energy work with wastewater treatment plants. We brought him in to present training at the MWOA summer meeting this last July, and he had developed essentially an aeration model that can be used for evaluating changes in your plant, to look at what are the savings that you can achieve. And the model can be used for changes like improved higher efficiency blowers, more appropriately sized blowers. It works well with looking at adding dissolved oxygen control or improved set points. It can be used to evaluate different diffusers or changes in system load or treatment requirements, including adding anoxic zones or improving primary clarification or settling with primary clarifiers. Next. The tool is essentially an Excel spreadsheet that uses your plant operating data to estimate how much air is needed, and from that, what does it cost to generate. Next. The kinds of data inputs. It calculates essentially monthly air requirements, or that's the way it's set up. You can do more than that if you want to put more work in and modify it. But things like the plant flow, the DOD load, nitrogen load or ammonia load, what are the DO levels that you have in your plant at different times of the year, what's the water temp, and then what's the airflow now and blower hours to create a baseline. Some of the other inputs would be more plant characteristics. What's your cost? What's the size of your aeration basins and depths of your diffusers? Basically, a number of things, and I think most of this information is information that is readily available in DMRs. Is that fair to say, or? Some people say so. But anyways, are there pieces that would be hard for you to come up with? Next. And then this is some of example results from some of Steve's work, what he did, and this is basically an excerpt of the output. You would have more information that you could look at, but this is kind of the results. We'll basically have the baseline of, in this case, operating with uncontrolled DO or manually controlled DO with essentially blowers that works out to be roughly 45% efficient. The first change that he looked at was going to higher efficiency blower, and savings there were, for this particular plant, were estimated to be about $44,000 a year. And then the last one was implementing dissolved oxygen control, going from an average of 4.1 parts per million to a controlled 2.5, and that in this particular case looked like it would save $74,000 a year. This would be a relatively large plant, probably in the 5 to 10 million gallons, if I remember right. But anyways, we've got the model that Steve presented in training. We're trying to use it in some of the assessments where it makes sense that we're doing. If there are any of you that would like to try using it, we would be happy to share the model with you and try to help you with any evaluation that you've got. So let me know. I do have some cards here, or give me your card if you're interested in learning a little bit more about the model. I'd be happy to share. We'd love to see it used as a tool to evaluate what the cost effectiveness of changes would be. Next. Let's see. Time. One of the other things or opportunities that we saw was dissolved oxygen control. The opportunities are when the load changes overnight. Doesn't happen with all plants, but if you're primarily a residential load or a commercial load where both your flow and load drop all off at night, DO control can save. If there are seasonal variations, that would be another place where DO. I guess the other opportunity is if in manual control there's just a large safety factor of high DO. There's some opportunity in terms of making improvements there. The kinds of potential savings that we saw at the plants that we looked at range from about $5,000 a year to about $15,000 a year. The project we had with Rogers, with an intern project, they're in the process of installing dissolved oxygen control at this point, and they're looking to save about $15,000 a year in electrical costs. There are a number of factors that have to be accounted for. The blowers have to be the right size. If the blowers or your aeration equipment is already operating at its minimum, it's hard to get any lower with DO. And you do need the controls and reliable sensors. The next. Other kinds of opportunities. One of the things that we saw with the benchmarks is the plants that had triple filters had pretty low aeration operating costs, or certainly lower than many others. So I realize that that's an extra operation and certainly more capital if you're building one, but if you're revising your plant, if you can keep the trickle filter in your system, I guess that would be my recommendation, at least to seriously consider that. Fine bubble aeration is certainly more efficient than things like jet aeration or coarse bubble aeration. Reduces the demand. One of the things that can be overlooked would be, does your system have leaks? Anything that you can do to find and plug leaks in the distribution system is reduces the load on your blowers. The other thing is to try to use a most open valve strategy where the distribution is going to different places. Basically, it's trying to cut the resistance in the distribution and basically having the blowers or your aeration system operate at the minimum pressure that it can that's actually needed, and reduce the head losses from using control valves. Yes, so just on the pumping efficiency, there are some ways to evaluate pump efficiencies. Basically, looking at what is the flow that's provided, divided by the head, divided by energy, gives you essentially a pumping efficiency measure. And if you look at the different pumps and give a guide or look at this pumping benchmark, you can get a sense of which pumps may be less efficient in your plant, and that may be worth taking a more serious look. Next. This was some relatively crude analysis that we did on a couple of lift pumps stations where the plant had concerns that one of the lift pumps in particular wasn't running as efficiently. I guess what we ultimately found was that these tended to be winter measures. These were winter measures also, where there was essentially low efficiency, and I guess the apparent efficiency, pumping efficiency, was tracked back to resistance heating in the lift stations as being what caused that apparently low pumping efficiency. That's a little bit different problem. There can be some solutions to that, but it was useful information. Next. In terms of general opportunities, I guess one of the recommendations that I would make or urge people to think about would be using your SCADA system to generate real-time benchmarks for your plant. You're measuring flow. You probably are measuring at least amps, and maybe you're measuring kilowatts. Have the SCADA system essentially combine those to give you a benchmark so that you know what your plant is running at any time, and so that you can look at trends over time. Is your plant improving? Can you connect it, poor performance, to certain types of operations and look at that? If you've got a demand charge on your electrical bill, I think it would be important or useful to track plant demand on a real-time basis. There are some plants that use that to lower demand charges, and essentially be careful about which equipment they're running at the same time, and plan their operations to avoid peaks in demand, and essentially load shift. I think there's also a lot of possibilities with SCADA systems to benchmark individual pieces of equipment that are important. So blowers would be an example, where you're measuring in many cases amps, and then many of the plants have airflow measurements. have the SCADA system combine those to give you a real-time measure of what is the air generation efficiency. And I guess we'll go to the next. So in terms of the savings that we've identified with this project, identified what we think are about $200,000 a year worth of savings at 4 plants, where the intent is to do assessments at 10 plants. 4 have been completed with reporting out and everything. There's 4 more that are in progress, but these savings are for the 4 plus 1 intern plant, or 1 plant where there was an intern. In terms of implemented savings to date, there's been about $20,000 of implemented savings, and then there's 15,000 that are being implemented as we speak, that are in process. It's the other comment I'll make. We've got 2 assessments that have not been started. If there are any of you that would be really interested in having an energy assessment, let me know, and we can talk about whether that makes sense and would fit into the project. And this is my contact information. Again, I've got some cards up here. I'd be happy to give that to anybody who would be interested. If anybody wants a copy of this presentation, you'd certainly be welcome to give me a card, and I'll send you a copy of the presentation. Any questions?